Hi everyone, thank you for joining us today. Non-parametric PDF estimation for advanced anomaly detection. Director and research data scientist at Thales will begin in just few minutes.
Can we start?
No, just, uh, in just few minutes. As a quick reminder, a brief survey will be shared to the end of this session. We invite you to share your best moments at the virtual conference on social media, Facebook, Twitter. Use the hashtag ODSC APAC. The post will be the highest number of likes and shares will win all access pass to ODSC East Virtual. All your feedback help us to shape your future conferences. Please join me in welcoming Kuldeep Jivani. We will now begin the session. Thank you, Kuldeep, for joining us.
Sure. So, good morning and welcome to my APAC friends. So, I'm Kuldeep Giovanni. So, I work as a research data scientist on data science topics. I also work as a director to solve some of the problems for the company. So, we are a company that spans in multiple countries. So, we are mostly focused on analytics. So, about that topic, I'm going to talk about non-parametric estimation for anomaly detection. Quickly, let me go to the agenda, what we're going to cover. So basically, I will talk about the navigation techniques. This is a very important industry problem, be it telecom, be it your railways, your space, your aerospace. We need these kind of techniques very often to take care of operations, to take care of the processes, to see when something is going bad, something is deviating. So anomaly detection is a very practical and important business problem to solve. And it is an unsupervised technique. So we don't need label data and we are able to make these inferences from the data itself. So talking about this talk, we will plan this talk in three phases. First, I'll talk about some of the standard techniques that we have available right now. Then I'll talk about how do we solve them statistically, what's the math behind them, and in different forms. Then I'll pick up a case study where the existing techniques are not good enough, and we need to do something more. So I'll present some of our research we did and publish a paper on that. And then I'll finally conclude with a practical way how you can use those advanced techniques which we apply in your own domain. So let's get started. So talking of anomalies, there could be different kinds of anomalies. Like a very simple could be a point anomaly. Just a simple point is different from the history. That's one way of seeing as an anomaly. Second could be a group of points are different from the history. Like in this case, there was a trend and suddenly the trend changed and now there is no longer any kind of trend available. That's a collective anomaly. There could be contextual anomaly. It depends on the context. Without the context, it may not be anomaly. So like if we, this happens mostly in case of multivariate data, where you have more than one KPIs. And in this case, if you see, we have two correlated KPIs over here. And for an example, I'm taking like a CPU and a network bytes, two of the KPIs. And a very simple correlation, when you transfer more data, you burn more CPU. There's a strong correlation between network bytes and CPU. So that's where you see a relation between them. If you talk about this point, the right point over here, so if you just do a simple univariate addition, so from network bytes, this data looks to be normal. It's not, it's within the bounds of normal data. It's not an anomaly. When you from CPU, it's again normal, not an anomaly. But collectively, this combination in this context is anomaly because for when we transfer more data, we don't consume less CPU. This is an indication there's some data lying in the buffer, it's not able to process. This is like a contextual anomaly. We do more from different techniques. This is three types. So coming back, we focus mainly on the point and collective anomaly in this talk, and we can have two sets of approaches for solving this. One is statistical, and second is machine learning based. So we're talking about statistics. What we're doing is basically finding the probability models of the data or the PDF, probability density functions, and we are majorly talking about parametric methods, univariate series analysis, and data with single peak or unimodal data. This mostly relies on receiving knowledge, like what to measure, what not to measure, what kind of parameters you want to consider. Then there's other things like unimodality, other things we assume in self-analysis. In case of machine learning, we fit models over data. And this is basically building models looking for patterns data contains. Then these are mostly non-parametric and multivariate and mostly multimodal, these are the things. And we can auto-discover patterns and we take lesser assumptions, and we learn from data patterns. So in this talk, we're going to talk about the statistical techniques, both from parametric, non-parametric point of view, and cover machine learning some other talk. So coming to anomaly types, there could be different ways of defining anomaly. Like this is the most simplest one. Data is in a range, and one point goes out of the range. So that's like an anomaly we can see. But there's more types. Like for example, over here also one point is going out of the normal range, but doesn't cross the upper threshold. So it is still an anomaly, but not a threshold anomaly like in the previous case. Different kind of anomaly. Similarly, we again see the data, the whole range of data is changing. It's kind of an entire change in the shift in the pattern. So it's an anomaly of different kinds. So similarly, we could have more kinds. Let's say data was very high, varying earlier, but suddenly the variance goes down. So it's another kind of data. So we'll define a few of these and understand how do we solve these kind of problems from the standard techniques. So the types of anomalies, we can broadly define a few of these, like threshold-based anomaly, a pulse or a spike anomaly, a level shift anomaly, volatility shift anomaly, a trend change, a seasonal change. These are like the standard things we do usually. But there are some advanced techniques we can also apply, like if there is multimodal, what do we do? If we have complex forecasting models, so maybe using LSTM, so we are catching more complex data. So we'll do all those things. So in this talk, I'll quickly go through these basic types, what we do, and cover one advanced topic, that's the multimodal. How do we solve that problem? Let's proceed on this. Talking about the first one, the simple univariate case, the data is varying in a range. So we can just do a simple distribution of this, and we get a simple Gaussian curve. And we can say around the mean, we can count the number of standard deviations. Let's say we say the value beyond 2 sigma is anomaly, and we can easily flag the anomaly. So we can compute something called a z-score. That's basically the value minus mean by sigma. So this is a standard way of counting number of standard deviations from the value or the center of mean basically. If more than 2, it's anomaly. A simple case. That's it for a univariate anomaly. If let's say we have multiple anomalies, we can extend the same technique to multiple dimensions. And from the edge bars, we have now a circle. So like when we, if both the papers correlated and have a single peak, it's unimodal, in that case, we basically get a region and values outside the red circle are anomalous. That's a simple way to find extend this in multivariate format, but using unimodal assumption. Talking about the other cases, like this one which we saw earlier. So this point is also an anomaly, but doesn't cross the threshold. So we have to do something else. What we can do, we can apply transformation to a data. A simple transformation could be just do a difference of the series. As you can see, the data difference between consecutive points. If we just plot them, we'll see the data varies in a range, the difference varies in a range, and then we again get a spike. So now we basically can bring this problem back to the same use case that we saw earlier. This series, the transform series, can now again be applied to a distribution. We can find the 2 sigma bounds and flag the anomaly. So we can this way also catch a spike and a pulse. If you look at some more complex cases, it's where the entire level is changing. So this is another kind of a use case. But here it's not more of a point case. It's more of the entire trend. So we can't use a point-based technique. So we'll use windows to solve this. The idea being we have like a running window. So we can have two sub windows and let's say green and a red one. And now we move this window across the data. And as we move, what we can do, we can find the mean of both the windows. So let's say mean of the green window, mean of the red window. We can find the difference between them. So if we just run this, we see it will continuously plot the difference of mean in the plot below. And as we reach this point of change, so as the red window is changed, so the score or difference increases. And at the moment where basically the green is exactly on the left side and then right side, we get a peak. This way, we can transform this, again map it back to our z-score based approach and apply a threshold to find the anomaly. Similarly, let's say we have this another example where the data waves are changing. We can again do a similar transformation. We can again let's say use two windows. And now this time, instead of doing difference of means, we can do difference of standard deviation because we want to find is the variance changing or not changing. So we run this again. We will see that the variance is in some higher range before this, and at this moment it increases, and after a point it just goes down again, and then it to a lower range. So we can then again apply our standard way of setting a threshold on this difference of standard deviation series. and find the anomalies again. So these is like some kind of things. Another way, let's say we have a trend in data. So calling such an use cases, we can do a simple linear estimation and set a linear model on this one. So if you set a linear model, what you can do is just take the difference of all the points from this linear model that you estimated and just compute the residual. If you compute the residuals will vary in some small range, and this point where we saw a large deviation, we get a spike over here. And again, now this comes down to the same standard problem of setting the set threshold on the bounds and flagging the anomaly by using the same Z-code AD methodology that we found earlier. If we have a more complex data, like where we have seasonality, so over here, so what we can do, first find a model that describes the seasonal part of that. So we can find, let's say, kind of a cyclic pattern which fits on this. So we can find first the period of the data, find one cycle, and do a statistical estimation of the values of that cycle. This way, we'll get an estimate of what is the natural periodic form of the data. It has been a pure data. And then for our purposes, again, take the residual and analyze the residual series. And this again now can be solved by the same way, finding a Z-score threshold on the residual and actually getting the anomaly points again. So now we can even combine these two. So if we have let's say data with both of these trends, a linear trend and a season one, we can first depend it and then take out a season, again get residual, and yeah, apply the Z-score threshold. So all of these techniques or different varieties of anomalies, as we saw, we can do some transformations and bring it down to something what's called distribution, and then try to solve the distribution. In all the examples, we use a normal Gaussian distribution to explain the concept. But the important point is all these statistical techniques rely on distribution, which is basically the expected probability density of a random variable. So when we talk about anomaly, what we are saying is basically the p-value or the probability value of a point is below some threshold as per the PDF or the probability function of this random variable. How does random variable is created? What is basically random in that? So the randomness can be comes from the expectation, or basically if you assume that the random variable or the series is stationary, then we can expect it to be basically varying around some kind of a mean, like a Gaussian distribution. So that's because the expectation was random variable and such a Gaussian distribution. In other cases, let's say the expectation comes from continuity of some pattern, like trend, seasonality. In that case, our variable could be the residual. So like the origin data minus the pattern that we are subtracting. Another case could be where we are setting a model, let's say using a forecasting LSTM, then the reconstruction error could be random variable. In that case, we are trying to see how basically we are able to see the differences and the error between them, the error between the predicted value and the actual value. That becomes the random variable. So in nutshell, all in all, it depends on the distribution of the variable. What we're talking about is distribution. So this is what the underlying statistical technique used by all of them. So now let's come to the next part of this talk where we talk about the distribution and let's get into small things that we will do from these distributions. The first is a parametric form. Like we know predefined what distribution you're going to take, like Gaussian, as I've been taking in all the examples earlier. There are more parametric forms like log normal, total data, discrete data with negative binomial, the geometric, and there are lots of these such examples. These are like available to us in the your all the different techniques available on the internet. But we are assuming things over here to be some form, but the real world is more complex. It may or may not follow these assumed trends that we are estimating. So we need to do something more. This is an example of a real world distribution. It looks like kind of matching to some of the ones you've seen earlier, but not exactly. But in some cases, we can approximate to a known form. Like in this case, if I put this green curve on this, and this is like a positive variable, along always bigger than zero. So I'm interested only in the right tail anomaly. And as you can see in this diagram, the green curve closely fits the blue curve at the right tail. So I can still use this green curve for anomaly detection, and I can still get my answers, which will be close to the actual one. And this is but an approximate form in distribution. So we can do this technique. But can we do this always? May not be. Let me show you a real case study which we found in one of our data sources. This is actually a KPI on a telecom network. So how people are behaving. This is something real pattern that we see over here. So if you use our standard technique like the parametric estimation, I just do the regular Z-score method over here, find the mean, so the Gaussian distribution, and do a 2 sigma deviation. So the red bars So the value is less than 2 sigma, given 2 sigma. And if I just plot the same bars on this times this chart, it says everything is inside the bounds. So there are no anomalies. So as per the normal science technique, the data is all fine. There is no issue. But let's say we have more smarter techniques where we can estimate the distribution from data. That's where the non-parametric form comes in. So I'll first show you a distribution which we have obtained via looking at data or fitting from the data. So this one below is like a non-parametric estimation of data, where we got the PDF or the density function of this data from this data directly. If you just look at this plot, you can make sense. So like you see two peaks over here. And as you can see, there are like two bands. There's an upper band and lower band. So there are definitely two bands of bands which is in data, and the upper band has more data. So the later peak is higher, and the earlier peak is smaller. As you can see visually, the lesser points in lower band. And you can also see the range, like the data is between 280 to 300. Over here also the peak is between 2 to 300. Similarly, the band here is like 380 to 400, and the peak here is around 380 400. So you can visually confirm that yeah, this distribution makes more sense for this data. Now let's say we use these kind of distributions for our anomaly detection purposes. So we can do a more better job. How? Let me show you an example on this. So if I place these markers on the lower chart to basically mark the low probability regions and just flag them. So now if you look at the points which are flagged by marking these markers on the above chart, so you can see firstly we are also able to find some of the edge cases that are near the thresholds which are not really having significant probability, but we are also finding set of points between them. If you see the points between these two orange lines, they are also very least likely to happen. So the trend is data most likely will have two levels, either upper or the lower level. And in between, it could be some noise, like the points over here, but the ones in between exactly have a very low chance of happening. So all these are also actually anomalies. The one exactly in between two of them, and this band can confirm them. So in short, by learning from data, we are able to make more better judgments about the anomalies, which statistically doesn't make sense. So the probability of these occurring is very low. So these are also could be of a business importance that could help us in solving more complex business problems. So, but in reality, uh, you could find the answer from the description which is shown you below. But why don't we do this thing? The reason is because to find a distribution which fits this data exactly, it's not easy. So let me just show you the same data can be viewed from different distributions. So all these four charts are basically distribution of the data, but by different methods, different techniques. One is like the simple Gaussian distribution, which we discussed in the earlier slide, and the below one is which we just discussed in the previous slide. And there are some other variations which we can see. So we can have different density estimations based on different parameters or different algorithms. Uh, but how do you choose which is the best one, and how do we get to the one which is closer to the data, and how do you verify? And it's not really easy, and that's where probably you need to do something more smart and more smarter things. If you use your default packages in Python and R, so the normal density function in R, you use a function called algorithm called Silverman, and Python use something called Ascot. Both of these are kind of similar algorithms, but just with a difference of scaling factor. So they, as you can see, can't do a good job. There are some advanced techniques like the shadowing zones, which is like a DKI method, which does a better estimation. There are lots of techniques, but shadowing zones kind of stands out, and it has done a quite good amount of job. And if you run this, you can see that it does really a good job. You can access this by density function using SJ. And in Python, we have this library called KDPY. But in real world, at some point, even these are not sufficient. The actually data is so noisy that we are not able to estimate the right period. So this mostly happens because there are lots of variations happening in data, too noisy, or data is not, we don't have a sufficient sample. So to solve these cases, that's where probably we did our research, how to improve on maybe shader zones. And then, so this is a paper that we published earlier this year. The idea is we can use a cost function to estimate the most optimal bandwidth and in nutshell, the density function for that. So this cost function will give us the minimum cost and that gives the optimal bandwidth. So bandwidth like the smoothness of the data and tells you what is the right kind of thing to fit for it. So I'll just, if you just summarize in a nutshell, this whole what we are doing over here is we computing a weighted mean absolute error. This is the cost function. So it gives a reference where the histogram is a reference. So, and from that you can see how much error we are making in our estimation. And as you know, histogram is essentially to the width of the bin. So we can convert this, the bin width to a function of h. So in short, we can convert everything as a function of h. That becomes like a cost function of h. And so this NAE can be then used with a weight. So this weight ensures we have a convex form. This weight function over here, this is a formula, is a quadratic form and a log form. And then we finally actually get this. So it comes to results directly. So if you use this technique, as you can see over in this chart, it's a heat map. Lighter colors where we are gaining from certain zones, darker where we are not. So as you can see, the horizontal effects is a Gaussian noise. As you keep increasing noise, this everything gets better. And for smaller samples, also this is better. So as you have more noisy data, this gets better than certain zones, and we can get a good estimate. So all this was till now to find the previous estimation. But I guess there's still one step missing. How do you find anomalies via them? So as a last step, I want to mention VDS is not really probability, it's probability density. Yeah. So the area under the PDF is equal to 1. And to get the probability, you have to integrate the PDF over a range. This is the probability for the region. Like in this area, the diagram, so the integration from A to B gives me the probability of the value between A and B. And in general, the probability of the point is 0 because as you know, if you reduce this width from B, that means B equal to A, the width is 0. So the area of this rectangle would be 0. So we can't find the probability of the point, and that's why we need to do something more. If you look at this diagram on the right, this is like for the same Gaussian distribution we were using earlier. So the area tells us the probability. If we are more than 3 sigma away, it's a 0.1% chance of this value. Similarly, for this 2 sigma away, it's 2.2% chance. So all these are standard ways. But for a general PDF, how do you solve that? For that, you have to do some integration. So we can estimate the value of x by doing small integration. Take a very small dx after x and do an integration x from x plus dx of the PDF function. This will give you an estimate of the value. So whatever the PDF is, if I do a small integration from a small delta interval and just see the value between that, it will give you an idea. Yeah, this is my last slide, and I'm just concluding after that. Yeah. So in short, so we have these two ways to find the probability from the PDF. One is the trapezoidal and Simpson rule. These are standard numerization techniques you can easily find the probability. If I summarize the whole picture, what we learned is basically we can discover the true PDF or close to true PDF from data by adjusting the right bias and the right variance basically. So these techniques can help us find the PDF. From this numerical integration, we can find the probability. In short, we can do now probability estimation for all real world databases. This was all I had to present, and I'll open it for questions now. Thank you very much for listening.
Thank you everyone for joining us today. Thank you for speaking, Kuldeep Jiwani. We are very grateful to those who have attended this session and will now start our own survey, short survey. This survey helps us to shape future conferences. Thank you. Thank you for joining everyone. Thank you.